Okay, excellent. So let's move on to the next talk. And the next speaker will be Zhang, who is going to talk to us about the elliptic double box and its symbol. Please go ahead.
Yeah, thanks for the introduction. And first, let me thank the organizer for the opportunity to speak. Today, I will talk about the recent work about the elliptic double box integral with Alexander Christensen and Matthias Wilhelm. So let me start with introduction and motivation. So in recent decades, incredible progress has been achieved in computing Feynman integrals and scaling amplitudes, especially in the planar enforceable Yamir theory. The current status of amplitude computation is summarized in this table. And as shown here, the 6 and 7 point amplitudes has been fixed up to a very high loop orders through the bootstrap program. And the 2-loop arbitrary and n-arbitrary amplitudes have been computed up to very high multiplicity by using the Q-bar equation. However, except the 1-loop result, all these achievements are limited to the arbitrary and n-arbitrary cases, where the results are expected to be a class of special transcendental function, the multiple logarithm. So on the other hand, this is one reason why these amplitudes are more accessible. So the Prolog are equipped with a very powerful total symbol, and the symbol make a lot of things easier. So first of all, the symbol trivialize the functional equation of Prolog such that we can use it to simplify the final result. A well-known example is the dramatic simplification for the 2-loop hexagon remainder function. After using symbol, 17 pages of a function just simplified to a few lines. Secondly, the symbol also manifests the singularity structure of the Prolog, such that it's possible to build a function basis subject to the physical constraint like our first entry condition and statement relation, which are crucial for the bootstrap program. And besides, symbol also has a profound connection with cluster algebras. The element of symbol for the 6 and 7 point amplitudes are captured by the finite cluster algebra GR for 6 and GR for 7. As you may heard from the Anastasia talk, recently there is also progress on understanding the relation of higher point amplitudes with cluster algebra of infinite type and Poisson-Grassmannians. And of course, symbol are not only used for the amplitudes in enforceable Yamir theory. Similar technique also used to bootstrap the form factor and combined with differential equation. Symbol are also used to bootstrap some Feynman integrals. However, we all know that general amplitudes are much richer than Prologs. For example, as Albert discussed, the Banana diagram relevant to the self-energy of electrons contains a Calabi-Yau manifold, and even in planar enforceable Yamir theory, Calabi-Yau manifold appears in the Zhang theorem. So in this talk, I will focus on the simplest Feynman integrals in planar enforceable Yamir theory, which is beyond Prolog. That's the 2-loop twin-point double box integral. So this integral is a dual-conformal integral. Its kinematics is described by 7 cross ratios of planar variables. And this integral is a special component of 2-loop twin-point and cube arbitrary amplitudes. So some concurrent joints from these integrals may be applied to the entire amplitudes directly. And there are several ways to show that these integrals contain a Lie curve. For example, using the differential equation, analyzing the Lie singularity, or just integrate indirectly. Here, let me give more details about the emergence of elliptic curve. So first, by using the of the Merlin transformation, one can show that the derivative of the box with respect the cross ratio U5 gives a 1-loop hexagon integral in 6 dimensions divided by a square root of the Gromman determinant delta 6. And the fact that this Gromman determinant is a cubic polynomial in U5 indicated the appearance of elliptic curve. Another way to show that is direct integration to the directly integration in the Feynman parameter representation. Then all Feynman parameter but one can be integrated out and it gives a with 3 Prolog and divided by a quartic polynomial. And again, this quartic polynomial shows that there is an elliptic curve. So the obstacle to perform the last integration for both cases is apart from these elliptic curves, there are also actual square roots in appending Prologs. So this is the first motivation for our work. Could we get rid of this elliptic curve? If we could, then we can compute the double box integral as iterative integral on the elliptic curve, or more precisely, the elliptic logarithm, which have been studied for a while. Then a natural question would be, what's the singularity structure of the box, or what's the symbology? For example, what are the symbol letters, and how can we manipulate the symbol? And are there any analogs of first entry condition and Sedgman relation as we have for the normal Prolog? So in the rest of the talk, I will quickly review the elliptic logarithm. Then I will show that the first problem can be fully solved by a variable substitution. And for the second problem, although the symbol is not fully understood, but we will see that this, the symbol shares some nice property with non-elliptic cases. So let me start with Prolog. So this Prologarism iterative function defined on the puncture sphere and with this d log 1 form as integration kernel. And for each Prolog, we can define its weight by the number of integration. And due to Ganchoff, each Prolog can be mapped to a tensor product. That's a symbol. And the symbol map can be defined by using the differential formula of the Prolog. So the total differential of Prolog is given by a sum of Prolog of lower weight multiplied with some d log. So the symbol can be recursively defined by replacing this product with tensor product. And the argument of this d log are called symbol letters. Another good property of the symbol is the first entry of the symbol indicated the location of branch cut. So in this way, symbol also manifests the singularity structure of Prolog. Symbol is also easy to manipulate since it's a tensor product and the symbol entry are just some algebraic functions. So to generalize the Prolog to the elliptic Prolog, one way is to include the elliptic curve directly in the integration kernel. Here, without loss of any generality, we consider elliptic curve given by a quartic equation. On this elliptic curve, we need infinite many integration kernels to make a complete basis. Here are only list 4 of them, which are relevant to the double box integral. With this definition of integration kernels, it's natural to introduce the so-called E4 function. So the advantage of this E4 functions, they are directly related to the computation of Feynman integrals, but it's hard to compute their differential due to the appearance of elliptic curve. And more importantly, this function are not pure. So usually they are just intermediate step of the computation. So from the perspective of mathematics and string theory, another natural generation is extend the genus from 0 to 1. So instead of considering the iterative integral on the puncture sphere, we turn to the iterative integral on the puncture torus. There are several versions of such iterative integrals. The one we will use is called gamma tilde function, and whose integration kernels are generated by the assistant chronic series. This gamma tilde function are manifestly pure by definition, and for each gamma tilde function, we can define its length by the number of integration, and we can define its weight by summing the up value of these indices. It's easy to compute the differential for this gamma theta function. And as we did for the Prolog, we use this differential formula to define the symbol for the gamma theta functions. And the symbol letters are primitives of the one form appearing in this differential formula. Note that these symbol letters are a quasi-periodic function on torus. And it's well known that the tori and the elliptic curves are essentially the same. And for elliptic curve of standard Weierstrass form, the map from the torus to the elliptic curve is given by the well-known Weierstrass P function. And the inverse map is given by the Abel map. So for our case, the elliptic curve is given by a monic polynomial of degree 4. So we first using the rational point at infinity to find the standard Weierstrass form. Then we find the corresponding Weierstrass map and Abel map. Here note that at each point in kinematics corresponding 2 points on elliptic curve, since it has 2 solutions on the curve and hence have 2 images on the torus. So with this bijection between the elliptic curve and the torus, we can translate the integration kernels for the EFA function to the integration kernel for the gamma theta functions. The process form are fixed by matching the pole structures. Now we have the all ingredients to put elliptic Feynman integrals into a pure elliptic log. So first we compute the Feynman integral as EFA function. Then we use these rules to rewrite the EFA function result in terms of gamma theta functions. Now let's see how to apply the technique of Prolog to the double box integral. We start with the dual conformally invariant Feynman parameter representation for the double box integral, which is a fourfold integral of some rational functions. 2 Feynman parameters, say beta 3 and beta 4, can be easily integrated out and leave us the V2 Prolog and a prefactor. The polynomial in this prefactor is cubic in beta 1 and quadratic in beta 2. And the 3 letters of this V2 Prolog are quadratic in beta 1 and beta 2. That means integrating over beta 2 not only introduce the elliptic curve, but also introduce some actual square roots. So to get rid of this actual square roots, we have to make a change of variable, and we find the following variable substitution do the job. And after this variable substitution, all letters of this V2 Prolog are linear in the new integration variable beta tilde 2. So now the integration of beta tilde 2 only introduce one elliptic curve, one square root, that's the elliptic curve. And we end up with a one-fold integral of with 3 Prolog and with dxy as integration kernels. And since all letters of this with 3 Prolog are rational in x and y, so now there is no obstacle to rewrite this G3 function in terms of EFA function and perform the last integration. So the resulting EFA function only has psi 1, psi 0, and psi -1 as its integration kernels. And this EFA function only depends on 26 arguments. And all these arguments, most of them are rational functions of cross ratios, but 8 of them containing 4 square roots. And all these square roots are arising from the 4-mass box subdiagram of the double box. Converting the EFA function result into the gamma theta function is straightforward. Just recall that the last integration kernel dx over y is simply dw on the torus time multiplied with the torus period omega 1. So after normalized by the torus period omega 1, the elliptic double box is a pure elliptic Prolog of length 4 and width 3. So now let's turn to the symbol. The computation of a symbol is straightforward. So initially, the symbol has millions of terms and consists of thousands of letters. But more importantly, all these letters are functions on the torus. So their relation are not transparent as the symbol letters for the Prolog. So to simplify the symbol for the box, so we first find the 30 linear relation among this omega 0 by using the addition theorem for the Weierstrass P function. And then recall that the integration kernel for the Power logarithm can be expressed as a linear combination of the integration kernel for the gamma tilde function. And this gives us the following identity. At last, by using the PSIQ algorithm, we find a 28 relation among a logarithm and if letters. Here I only gives one example, and currently we don't know how to prove any of these 28 relations. After using all these relations, dramatic simplification happens. First, all omega 3 just dropped out, and we find that there are only 7 different last entries, and all these last entries are simply elliptic integrals, and we reorganize the symbol according to last entries and denote the corresponding weight string function by these last entries. The first 2 entries are simply a logarithm of kinematics, and we find the symbol satisfies the same first entry condition as non-elliptic case. So the first entries are simply a logarithm of 7 cross ratios that we introduced at the beginning. And furthermore, we find the first 2 entries also satisfies a certain pattern. They form a symbol of lead to 1 minus u, log u times log v, or for my box function. So in this way, our symbol manifests the Schliemann relations. Apart from the 7 last entries, so the if letters only appear at the third entry of this with 3 function f plus. So in other words, the with 3 function associated with the other 6 last entries are simply Prolog. And the double box integral has reflection symmetries, and our symbol also manifests this symmetry. The first 3 terms in the first line is individually invariant and both reflections, and the first term in the second line generates a 4 orbit and both reflections. Recall that the derivative of double box integral with respect to U5 gives the 1 loop Hessian integral, and our symbol also manifests this result. Of 7 last entries, only the first one depends on U5, and the associated with 3 symbol are exactly the symbol of the Hessian integrals. So in this way, this differential equation becomes an immediate result of our symbol. So let me end this section by summarizing the symbol alphabet. So the symbol alphabet for the double box consists of 36 rational letters, 24 algebraic letters, and 20 elliptic letters. Comparing what we know from the 2-loop MH and NMH amplitudes, there's 2 new features. So first, the individual algebraic letters appearing in the 2-loop NMH amplitudes only contain 1 square root. However, in the double box integral, there are also algebraic letters involving 2 different square roots. The other new feature is definitely this elliptic letters. Apart from 7 last entries, so the other elliptic letters appearing at third entries only come in a 30 certain linear independent combinations. And currently, we still need a comprehensive understanding of these elliptic letters. So now let me conclude. So in this talk, I have discussed a special component of two-loop twin point and cube amplitude. That's the box integral. We verified that this integral is indeed the elliptic logarithm, and we computed the symbol, and we find that the symbol satisfies the same first entry condition and the statement relation as the arbitrary and unarbitrary cases. The elliptic letters appears, but only appear at third entry and first entry, and all last entries are simply elliptic integrals. So lots of interesting questions remain. First, we don't know how to prove this the 28 relation found numerically, and we don't have a good understanding of the 13 elliptic letters appear at third entries. For algebra letters, we can require them to be of this form, such that their relation only involve themselves. But for the elliptic letters, currently we don't have a similar definition, which are crucial for understanding this identity and these letters. Besides, how to lift the simplified symbol to a simplified function is another interesting question. So the fact that our symbol trivializes the differential equation relating the double box to the one loop Heston integral suggests a new way to bootstrap. First, we take the known symbol for the Heston integral and append this elliptic integral as last entries. Then the remaining terms can be fixed in principle by imposing integrability condition. So some other Feynman integrals, for example, the three-loop train check integral, also satisfy similar differential equation. We expect such a bootstrap program is available for this kind of Feynman integrals. As we heard from Anastasia talk, recently there's lots of progress on understanding the relation of algebra letters with the class algebra of infinite depth. So it would be interesting to extend this cluster program to including the elliptic letters. Last, we expect the technique developed here can also be applied to some to general elliptic Feynman integrals and help us to compute, even bootstrap the entire two-loop amplitudes in planar length for supernomial theory. Thank you.
Thank you for this very nice talk, Chi. Let's thank the speaker. And I can ask if there are any questions. Claude, please go ahead.
Yeah, hi Xi, thanks for the nice talk. It's a very nice computation. I have a question about your last entries. Maybe you said it. So you said elliptic integrals. Now, yes. I'm not quite sure what you mean by that, because, for example, when you talk about the algebraic entries, you implicitly mean they are d logs of these things. So they are differential one forms or logs. When you say elliptic integrals, you mean differentials of them? Do you mean, what do you mean? They are not at the same level as algebraic functions, right? They must be something else. They are not algebraic functions and elliptic integrals. They are d logs and some other differential one forms. So what exactly do you mean when you say elliptic integrals as letters?
Yeah, I mean, so in principle, that we just use the different formula, and the different formula will produce some one form, right, at the end. And we just use the primitive of this one form. So what we mean, the letters are the primitive of this one form. So they're function.
then in the same sense, your other letters should not be algebraic, they should be logs. They are the
Yes, yes, sorry.
primitives. So
Yeah,
I'm not sure if you can say that these last entries are elliptic integrals. They are differentials of them. Then those maybe themselves.
Yeah,
elliptic
yeah, that's
integrals.
correct.
The
Yeah,
thing.
yeah.
And
Yeah,
avoid
so
maybe the confusion.
yeah, sorry, but yeah, the other letter are simply logarithm of kinemax. Yeah.
Okay, thanks.
So are there any further questions?
May I ask a question?
Please go ahead.
You use the canonical Eisenstein theory. So I was wondering if the property of quasi-doubly periodic could simplify the calculation.
Yes. I think for example, we use this one to generating an identity to simplify the symbol.
Oh, so this is related to the doubly periodic property?
Yeah.
Okay. So what if you just use the pure doubly periodic functions? I mean,
here we perform this quasi-periodic because we want this function to be holomorphic.
Okay.
Yeah, that's the reason we use this quasi-periodic function, not the periodic double periodic function, because those one is not holomorphic, and so it's not current for our computation.
Okay, thank you.
Simone, do you want to ask?
Thanks. So thanks a lot, Shi. I really enjoyed your talk, very fascinating. So I'm interested in the idea of bootstrapping this thing since you now provided an alphabet. But I mean, I would immediately stop at the very beginning because probably I'm a bit ignorant, but how would one construct like iterable symbols out of this alphabet? Because so what I would do in a polylogarithmic case, I would take your alphabet, construct the iterable symbols, and then start putting constraints on that. How does it work here in this case?
I think here here we so the ideal case is we don't assuming extensions of alphabet, so we can just take the last two entries of we can take last two entry of these terms and just to solve a differential equation and to try to find the whole symbol.
Okay, so this is just because the elliptic letters only enter at the very end.
Yes, yes.
Okay, but if instead, I mean, more in general, let's say that we are not that lucky and we have to handle these letters also deeper into the symbol. How does it work?
Well, it will still explore this aspect, but here it's kind of, it's rather to say it's a symbol integration for the Prolog reason. Mm-hmm. And I think, yeah, as I said, we just, at the end, we just take the last two entries because, for example, for this one, we know the first three entries are integrable. So we just take the last two, and we just compute the second order partial differential and
No. Okay, no, that I understand. My question was really more general. It said that we don't know anything, like we don't know that the first three entries are given by the hexagon integral, for instance, but really we only know the alphabet. And
but I think the alphabet is hard question. Mm-hmm. I mean, for example, for this one, I really don't know how to just read of this symbol alphabet.
Okay.
Obviously, that's a hard question.
Thanks a lot.
So I have a question about the final answer for the double box integral. Is it clear from your formula or from the result that you obtain that if you take the limit, say in the dual picture where you take two legs together, can you see all the elliptic stuff drops out? Or do you have to do lots of work to see that actually you can rewrite it as polylogs?
Well, actually, it's a very good question. We have to do a lot of work because here we use omega-1 to normalize this double box. And these periods become 0 and the soft limit. So we need more work. For example, we need to consider another normalization, just normalize the box by the omega-2. That one has a small limit and the soft limit. And yeah, I think in that case, we can see this soft limit. Yeah.
Thank you. Okay, so let's thank the speaker again. It's time for the next talk. So thank you, Chi.